Okay, welcome to this first tutorial in electric power system for 2022. Here we are dealing with some problems based on the fundamentals of electric power and inductance calculation. So the first problem is like this. You have two ideal voltage source. So two ideal voltage source are there which are designated as machines 1 and 2. So here you can see that machines 1 and 2 are basically two ideal voltage source. What is ideal voltage source? Ideal voltage source is the one which is not having any losses. Now the generator voltage E1 and the generator voltage E2 are given to us, and the line impedance Z, which is the net drop in the line between the generator 1 and generator 2, is given to us. You have to determine whether each machine is generating or consuming the real power and the amount. It means it is not told that this machine E1 and E2 is either a generator or a motor. Simply the voltage source is given, but we are not knowing whether this is a generator or this is a motor, and we have to decide that. And then we have to say what is the amount of the power which is consuming or delivering by the machine. Second part, whether each machine is receiving or supplying the reactive power and the amount. So as you know that we are going to discuss in this lecture also, that the power, complex power S, is basically divided into two categories. One is the real power and another is the reactive power. So the complex power S will have two components. One is the real power whose unit is in watt, and the reactive power whose unit is in volt ampere reactive, whereas the complex power unit is in volt ampere. So P basically is the real power, which is the net loss in the DC part, that is the resistance. So if you have the resistance, what is the real power associated with it is P, and if you have any reactance involved, whether it is an inductor or capacitor, then that power is known as the reactive power Q. And the complex power S is basically P plus JQ, which is the real power plus imaginary terms of the reactive power. It can also be written as the product of voltage into current, where current we are taking the conjugate, okay, to include the direction of the current symbol. So we have VI conjugate is equal to P plus JQ. The P and Q absorbed by the impedance that we have to calculate. What is the real power and the reactive power for the impedance also. So these are the three different parts of the problem 1, which is a very fundamental problem, and we have to deal with the power and its direction. So let us see the solution. So first we have to calculate the current which is flowing between the generator 1, or rather I say the machine 1 or machine 2 through the impedance Z. Means what is the current which is flowing here. So the current which is flowing here is basically the differential of the voltage between the machine 1 and machine 2 divided by the net impedance of the line. This is in accordance with the Ohm's law. So the E1 and E2 value, that is the voltage for machine 1 and machine 2, is already given to us. The impedance of the line is also given to us. You can note that the resistance associated with the impedance of the line is 0. It means the net real drop usually in the transmission line is not there. It is the reactance which is basically governing over the resistance. So if you have the resistance and the reactance of the transmission line, then the resistance part is negligible, whereas the reactance part is the only one which is governing. So here we have J5 as the reactance between the source and the load. I don't say whether it is a source or a load because we don't know what is E1 and E2 here. Okay, now once we have determined the current which is flowing between the machine 1 and machine 2 is having a amplitude of 10.35 ampere and the angle is 195 degrees. So we can determine the complex power now. So as I said, that complex power S is equal to voltage multiplied with the conjugate of the current. So here the current is basically a complex quantity. So if I take the conjugate, I have the negative sign. So these I can write as P plus JQ, where P is the real power and Q is the reactive power. Now let us write the complex power equation S1 and S2, that is VI conjugate. Now, let us see the passive sign convention first. So, in the first year, we have studied in electrical science that if you have any element, so if I take one element where there is a positive symbol and negative symbol, if the current is coming out of the positive symbol and the current is entering the negative symbol, then we can say that power is basically the plus of voltage into current. This is in accordance with passive sign convention. Whereas if the reverse process take place where the current is entering the positive terminal and it is coming out of the negative terminal, then the power will be negative minus VI. So the power can be positive or power can be negative. This is only in accordance with the direction, not the magnitude. Whereas the positive power means that the power is absorbing in nature or there is a loss in the system. The negative power indicates that the power is basically delivered or it is generating. So if the power is delivered, then we can say that the power will be negative, and if the power is positive, then we say that the power is absorbing. So this is, we can write power is equal to product plus minus voltage into current, where voltage into current is basically the magnitude, or rather I can say I conjugate. The positive and negative sign indicates whether the power is absorbing or power is delivering. Now see what is happening in the machine 1. The machine 1, the current I is basically coming out of the positive terminal. It is coming out of the positive terminal. This indicates that we can say that the machine 1 is basically a generator, right? Because it is the source which is giving out the current. So I will be having a negative symbol here for the current, and then the power will be net complex power S will be equal to minus of VI conjugate. So if I have the power P1 plus JQ1 written in the form of real power plus reactive power, and then we substitute the value of the voltage and the current in the equation of this, we can have what is the real power and what is the reactive power. The unit being in volt ampere. So this is the real part and this is the imaginary part. Now going back to complex power 2, for machine 2, we have the current which is entering the positive terminal of the machine 2. It means that the power will be equal to plus of VI conjugate. Now we can write that in the form of P plus JQ. We substitute the value of the voltage and the current, which is current we have already obtained and voltage is already given. We will be getting that the complex power is equal to minus of 1000 minus J times 268, and the unit is in volt ampere. So if you note the complex power here in machine 1 and machine 2, you are having the real part is positive in machine 1, whereas the reactive power, real power is negative in machine 2. This indicates that machine 1 is basically generating the power, whereas machine 2 is basically absorbing the electrical energy. So I can say machine 1 is basically the generator, machine 2 is basically the motor which is taking the electrical energy through the line Z. Now we have the conclusion. Let us do the conclusion. Machine 1 may be expected to be a generator, as I said, because the current direction and polarity marking. So we can say that since the current is coming out of the machine 1, and we have also seen that the power is negative in machine 1 is basically the generator. Since power 1 is positive and the reactive power is negative, the machine consumes energy at the rate of 1000 watt and supplies reactive power of 268 volt ampere rating. So we have seen that the real power is 1000 watt, and the reactive power in the previous here you have a negative sign here, so it is minus of j 268. So here the unit is in volt ampere reactive, the total unit is in volt ampere. Now, since we have the positive real part, so positive real part and the negative reactive part, okay, or the imaginary part, we can say that the machine is consuming the energy at a rate of 1000 watt, and it is supplying the reactive power of 268 volt ampere rating. This negative sign means that it is supplying. This positive sign means that it is absorbing. So the real part it is absorbing, whereas the reactive part it is supplying. So the machine is actually a motor. So now, since I have said that the machine can be a generator or machine can be a motor. So what is the difference between a generator and a motor? The electrical energy is converted to mechanical energy, or the mechanical energy is converted to electrical energy. That can be the reverse process taking place in the machine. But in both way, we have to understand that whether the machine is operating as a generator or the machine is operating at a motor. So here, from the power equation, we have the S1 power is basically plus P minus JQ. It means the real power plus P is basically absorbing, and the reactive power Q is basically delivering. So if the reactive power is delivered by the system, whereas the real power is consumed, then it means that the machine is a motor. So here my first assumption was wrong. So here when I said that the machine 1 is a generator and machine 2 is a motor, how I said? I said that the current is coming out from machine 1 and current is going in machine 2. It means that machine 1 is a generator and machine 2 is a motor. This I made this assumption. But after calculating the real power and the reactive power, my assumption is wrong and the machine is actually behaving as a motor. Let us see the machine 2. Machine 2 is having a negative real power, whereas it is having a negative reactive power, minus Q2. Okay, the machine is generating energy at a rate of 1000 watt. Since it is a negative, it is basically generating the real power of 1000 watt, and it is also supplying a reactive power of 268 volt ampere rating. Both is negative, the P value is negative and the Q values both are negative, and hence it is delivering the real power, it is delivering the reactive power, both the power it is delivering. Hence we can say that the machine 2 is basically a generator. So the assumption can't be done only from the current. So seeing the direction of the current, we can't say whether the machine is basically a generator or a machine is basically a motor. We have to see the direction of the real power and the reactive power also to understand whether the machine is generator or a motor. Now let us see the supplied reactive power. What is the supplied reactive power? We have 268 plus 268. That is one from the generator, one from the motor end and one from the generator end. So the net reactive power is 536 volt ampere reactive, which is required by the inductive reactance of 5 ohms. So here it is J5. That is the reactance of the line through which the current is flowing between machine 1 and machine 2. So the net reactive power of 536 volt ampere reactive is basically required by the reactance of the line. Since the impedance is purely reactive, no power is consumed by the impedance, and all the watt generated by machine 2 are transferred to machine 1. So it means that the machine 2, which is a generator, machine 1, which is a motor, and the resistance part here is basically 0. So the power loss in the line is 0. The real power associated with the generator and the motor is basically taken from the 2 to 1, whereas the reactive power Q is basically taken by the transmission line. So these conclusions of this particular problem is very important to understand how the direction of the power is there and what are the associated real power and the reactive power. The last part of the question was the reactive power absorbed in the series impedance of the line. So you have the impedance Z where it is only the reactance, whereas the resistance is 0. I know that the power is basically, I can write I square into resistance R. So this is the real power. If I having the reactive power Q, this resistance will become the reactance. So I square X is basically the reactance of the line where X is equal to 5 and the current magnitude is 10.35 ampere square. So I'm getting 536 volt ampere reactive. So from here also it is very easy to calculate that 286 plus 286 whatever we were getting 268 or 286 from here, that is also combining to 536 volt ampere rating, and from here also we are getting 536 volt ampere rating. So that is the reactive power which is absorbed by the series impedance of the line. We'll go by problem 2. The terminal voltage of a star connected load. Now see, here we are dealing with the load. Star connected means that we have the load which is connected in the form of star. So this is the phase 1, this is phase 2, this is phase 3. So three phases are there for the star connected load, and it is said that three equal impedances are there. So if I say this one as Z1, this is Z2 and this is Z3, all the impedances Z1, Z2 and Z3 are equal, which is equal to 20 angle 30. Unit is in ohms because the impedance unit will be in ohms. Now the voltage is 4.4 kilovolt line to line voltage. Now for a three phase system, you should be having a line voltage and you should also have a phase voltage term. Okay, what is line voltage and phase voltage? That if you have a three phase line, that is line 1, line 2 or line 3, and there is a ground G. Sometimes we write this in the form of R, Y and B. So if I measure the voltage between the two lines, if I measure the voltage between the two lines, this is known as the line voltage. That is the voltage between the two lines. It can be the voltage between RY, the voltage between YB or the voltage between RB. Anything. The voltage between three lines. If I measure the voltage between a line V and between the ground, this is known as the phase voltage. Means a line and a ground is involved. Instead of a ground, I can write the neutral also. Sometimes what happens is that if you have a single phase system, like if you have a source voltage and then you have the impedance Z, and then we have a neutral point which is grounded. So this is a neutral which is a ground, right? So I can say this point is neutral which is grounded. So the voltage which is measured between the phase R and the neutral point, the voltage which is measured between the phase Y and the neutral point, the voltage which is measured between the phase B and the neutral point, these three voltages are known as the phase voltage. These three voltages are known as the line voltage which is measured between the two lines. Now let us discuss the current first. The current will also be the line current and the phase current. If the current is moving between the two lines, if the current is moving between the two lines like this, so that will be the line current. If the current is coming from the line and going to the neutral and the ground, that is known as the phase current. So in three phase system, it can be star connected system, it can be delta connected system. So you should know the relationship between the line voltage and phase voltage. You should also know the relationship between the line current and the phase current for the star connected system and the delta connected system. Now, let us have a quick revision. Line voltage is equal to root 3 times the phase voltage, and the line current is equal to the phase current for a star connected system. This is the reverse of that. Line voltage is equal to phase voltage and line current is equal to root 3 times the phase current for a delta connected system. So these relationship for the star and the delta, the relationship between the line voltage, phase voltage is very important for a three-phase system. Now these are basically the overviews. Let us come to the question here. So 4.4 kilovolt is basically the line to line voltage. Now here the impedance of all the three lines are equal. It means that VRY is equal to VYB is equal to VRB. The reason being is that the impedance of the line is equal, so the net drop in the line will also be equal. The impedance of each of the three lines connecting to the load to a bus at a substation is ZL is equal to. So this is the load impedance which is connected from the load to the bus end. Now what is a bus? Bus is basically a power system grid where it is connecting the generator, motor, transmission line, transformer, any devices which are connected to the bus or the power grid is the bus. So here the bus can be said to be a infinite. Infinite means that the voltage is infinite. So there would not be any voltage drop or there not be any voltage intake. Like an ocean, if you take a drop of water from the ocean, a bucket of water from the ocean, the water will not come out. So here the bus is basically that power grid. Find the line to line voltage at the substation bus that you have to calculate. So let us see the solution. So the magnitude of the voltage to the neutral. Now see, we are calculating the voltage to the neutral. Now consider that whenever you have a three-phase system which is balanced, balanced means that the impedance Z1, Z2 and Z3, which are the net impedance of the line, are equal, then the system is known as balanced system. This system is solved in single phase and then the result is transformed to the three phase. Now why we are solving the system in single phase? The reason being is that here you have three conductors, you have only one conductor here. So it is always helpful if you can solve the problem in single phase and then you transform the result in three phase. So first I will transform the line voltage to phase voltage. As I said that for a star connected system, your line voltage is root 3 times the phase voltage. So phase voltage will be equal to line voltage by root 3. So that gives to be 2540 volt. That is the voltage to the neutral for the star connected load. Now if Vn is the voltage across the load is chosen as a reference. Now we have R, Y and B. Three phases are there. You can write A, B or C. There are different names given, or line 1, line 2 and line 3. All the three things are same. Now as I said that the voltage, the system is balanced, so the net magnitude of the voltage will remain the same for all the lines R, Y and B, but the angle theta will be shifted with 120 degree. So there will be an angle of 120 degree between the lines 1, 2 and 3. So there will be 120 degree shifting between the phase R, phase Y and phase B. And now I have to take one phase as the reference phase. So reference means at 0 degree. So which phase is the reference? So if I take the phase A to be the reference, here I have written A, you can write R also, Rn. So if I take the voltage of Rn phase at 0 degree, the other phases Y and B will be shifted by 120 degree. So one will be at minus 120 degree and another will be at plus 120 degree. Then the system will be balanced, and this is a three-phase system. It means that the AC signal that is transferred for the three phases A, B and C. So A is at 0 degree. So B and C, if you have a negative sign, it means that it is starting earlier. If you have a positive sign, then it is starting late. So like these three phases will be there, R, Y and B. So once we know that, we can write that the voltage of the phase A is 2540, which is the magnitude, and angle is 0 degree. Now we can compute the current of the phase, that is the voltage divided by the impedance of the line. Now the impedance is single phase, voltage is also single phase. So we are dividing the single phase voltage with single phase impedance. We are getting 127 angle minus 30 degree as the net current associated with the phase A. So the line to neutral voltage at the substation, now we have the voltage, we have the current. Now ZL is the impedance which is connecting the load and the bus. So this side you have the bus, this side you have the load. So ZL is that impedance which is connecting between the bus and the load. I can have the drop as Vn plus In into ZL, that is in accordance with the Kirchhoff's voltage law equation KVL. Now I can substitute the voltage, current and the impedance. So you can see that all are in phasors, with having a magnitude and direction in angle. Net answer is 26670 angle minus 2.70, that is the line to neutral voltage at the substation. So in this way you can calculate. Now this is basically single phase. So I said that whenever you have a three-phase system, you are going to solve in single phase and then you back transform the single phase result into three phase. Now 2670, this is the phase voltage, and I know that line voltage is equal to root 3 times phase voltage. So my net answer will be root 3 multiplied with the magnitude of the phase voltage, which gives me 4.62 kilovolt. That is the magnitude of the voltage at the substation bus. So what we are getting, that the bus is delivering the power of 4.62 kilovolt, and at the load end you are getting a voltage of 4.4 kilovolt, and there is a net impedance ZL through which the power drop will be there. So here we have marked all the power, voltage and the current in terms of the electrical quantities, where how the power is being transferred from the source end to the load end of the impedance, that is being shown. So you have to represent the result in the form of voltage, current, impedance of the line. Okay, in this way you can take all these quantities. Now, two problems we have solved based on the power calculation fundamentals. Now, another few questions we are going to solve on the inductance. Find the self GMD, that is geometric mean distance. Self GMD, the other name is GMR, geometric mean radius, for each conductor configuration shown in figure. So there are two figures, A and figure B. Two figures are there. You see 1, 2 and 3 represent the three-phase lines. So three conductors are there, 1, 2 and 3. Both A and B, or rather I say A and B, are of different configurations. So the configuration of the conductor or the arrangement of the conductor is different for the phase A or the, I can say, line A or line B. Radius of each conductor is 1 centimeter. So if I measure the radius R of each conductor is 1 centimeter, I have to obtain the GMR, that is geometric mean radius. The other name is self GMD. Let us see the solution. First we'll take the configuration A. This is configuration A. The basic formula for GMR, that is geometric mean radius, is under root you have the number of conductors, that is n. So here you put n, that is equal to 3. 3 conductors are there, and then you have to calculate the configurations 1, configuration 2, and configuration 3, because 3 conductors are there, so 3 configurations will come for the individual GMR. Now 1 and 3, if you see, both are identically placed, so the GMR of 1 and 3 will be equal, that we have to calculate. In inductance, we know that R dash, that is the fictitious radius, is equal to 0.7788 multiplied with the actual radius of the conductor. So we have to calculate the GMR1 and GMR3, both will be equal because of its configuration, its placement. So we calculate that with respect to the distance. So what is the distance between the two conductor? So here, if I take this one as 1 and this one as 2, these distance is r and this distance is r. So the net distance is 2r between 1 and 2. So we have to calculate the GMR of 1 and 3 separately. We will be getting the GMR of 1 and 3 as 0.0184. Then we can calculate the GMR of the second conductor, which is equal to 0.014604, and then the net GMR of all the 3 conductors with the formula of the cubic root of GMR 1, 2 and 3, the product of that. We are getting 0.017036 as the net GMR of the 3 conductors. This is in accordance with the configuration 1. Now if I go with the configuration 2, then let us see the configuration 2. Here we see that 1 and 3 are equally placed, whereas 4 and 2 are equally placed. So both are having the same placement. So GMR1 is equal to GMR3 and GMR2 is equal to GMR4. I can calculate that separately, GMR calculation, and I will be getting the result for GMR1 and 3 equal, GMR2 and GMR4 equal. Then I will calculate the net GMR of the conductor. Since there are 4 conductors involved, so we have the fourth root of individual GMR of 1, 2, 3 and 4. The answer is 0.016921. We should know to calculate the GMD and GMR, that is geometric mean distance and geometric mean radius, because these will be helpful in calculating the value of the inductance L, which will be useful in calculating the value of XL, that is the inductive reactance of the line. We will see in the coming problem. Let us find the inductance of a 3-phase line operating at 50 Hz. So the frequency is 50 Hz and the conductors are arranged in the figure. So this is a 3-phase line. We have phase 1, phase 2 and phase 3. The conductor diameter is 0.8 centimeter. So diameter is given, it means the radius is equal to 0.8 divided by 2. So the distance between the individual conductors are also given. We have to find the inductance. So finding the inductance means that finding the GMD first, then GMR, and then we can calculate the inductance. So previous problem of calculating the GMR will be helpful in solving the problem 4. So let us find the GMR of the conductor. All the 3 conductors are of equal radius. We know that the value of R dash is equal to 0.7788 into the radius of the conductor. This is known as the fictitious radius of the conductor, which is due to the magnetic field associated with the current carrying conductor, and we have the skin effect. So this principle is well taught in the lecture class. What is skin effect? And then we have the GMR is equal to 0.0031152, which is coming from 0.7788 multiplied with the actual radius. Then we calculate the GMD of the line. Now, when you calculate the GMD, we have discussed in the lecture class also, it will be the product of M into N. Okay, the product of M into N, how many conductors are there and how many we are taking. So we have got the GMD as equal to 2.0158, and then the inductance of the line is basically 2 into 10 to the power minus 7 ln of GMD by GMR. Now here we are taking the natural logarithmic ln, okay, natural logarithmic of the calculation of GMD by GMR multiplied with 2 into 10 to the power minus 7. And now understand, this is the phase value per phase. If we have the three-phase system, we have to multiply this with 4. So here the unit is a millihenry per kilometer. We are getting 1.294 as the net inductance of the line. So once we calculate the GMD and GMR properly, then only we can get the inductance as the correct result. Problem 5th, a 500 kV line has a bundling arrangement. So what is the meaning of bundling arrangement? That number of conductors are more per phase, and 2 conductors per phase is there. So each phase will have 2 bundled conductors. Compute the reactance of the line. Now understand, here the reactance is asked. Whenever reactance is asked, it means XL value. XL is equal to omega L, where omega is equal to 2 pi f multiplied with the inductance L. Per phase of this line at 50 Hz, each conductor carries 50% of the phase current, assuming full transposition. Now transposition, we have taught you in the lecture class that if you have the three-phase line R, Y and B, then every 1/3 of the net line, so if the net transmission line is of length L, then after every L by 3, the position will change. Okay, the position will change in such a manner that the net inductance is remain conserved. Okay, so after every L by 3, there is transposition of the line. So what we have to calculate, the reactance XL for these bundled conductors. So 2 conductors are there in the bundled. So this is the phase 1, this is phase 2 and this is phase 3 with 2 bundled conductors. The diameter is given to be 30 mm for each conductor, and the distance between the center to center for the bundle conductor is 0.5 meter, and 15 meter is the distance between the two phases 1 and 2, and between 2 to 3 also there is 15 meter distance. So the geometry is given to us. We have to calculate the reactance. The voltage is 500 kilovolt. Now let us see, the distance is 15 meter which is there. Now this distance will be 30 meter between A and C. This is C and this is B. So we have to calculate the method of GMD, that is geometric mean distance. We have to calculate the distance of all the conductors, and then we have to find the net GMD, that is D equivalent of the conductor, and the GMR of the line. So these I will not discuss. This is well taught, the GMD and GMR calculation of the line. Only difference is that this is a bundled conductor from the previous arrangement. If the conductor is not bundled, you will be having 3 configuration like this. Since the conductors are bundled, you have 2 conductors per phase. So once you calculate the value of GMD and GMR properly, then you can obtain the inductance of the line, and then you can calculate the value of XL is equal to omega L, that is the net reactance of the line. So XL we have calculated inductive reactance, and that is per phase basis. We are getting ohm per kilometer 0.346. Now why per kilometer? Because the net length of the transmission line is not given to us. So what we do is that we calculate per kilometer the parameters, that is the inductance and the capacitance. Capacitance will take later. Now we are focusing on the inductance of the line. Now the problem 6th, we have a double circuit 3-phase line. So we have 3-phase and a double circuit. Double circuit means that 3-phase line is here and 3-phase line is here. These are the double circuit. Single circuit, and this is the double circuit. So we have A, B and C, the individual phases of the conductor. So you have A, B and C. This is the double phase. So we have A dash, B dash and C dash. Now the distances are given 1 meter and all the configurations are given. Radius of the conductor is 1.5 centimeter. That is also given, and all the conductors are equal. The radius is equal. You have to obtain the inductance of the double circuit line. Whatever the calculation we are doing, if we obtain the GMD and GMR appropriately, we will get the inductance correct. If the GMD and GMR is mistake is there, the inductance will not get correct. Now let us see. First we calculate the value of the GMR, that is the R dash or the 50 CS radius. First R dash is equal to 0.7788, that is R. Then we calculate the value of GMD between DAB, DBC and DCA. Okay, all the phases. So A, B and C are three phases. We have to obtain the GMD between A and B, GMD between B and C, and GMD between A and C. This we have to calculate. Once we get the GMD, we can get the GMR from the 50 CS radius that we have calculated as the value of 0.187. So the cube root, because we have three conductor of GMR1 multiplied with GMR2 multiplied with GMR3. So we got the GMD value, GMR value, and then we can substitute in the equation of the inductance. We'll get the value in unit millihenry per kilometer per phase. So we are obtaining per phase basis. Inductance is per kilometer because the length is not given to us. The parameters are all per kilometer. This is the final problem for today's tutorial. Calculate the 50 Hz inductive reactance, that is XL, at 1 meter spacing in ohms per kilometer of a cable consisting of 12 equal strands around a non-conducting core. A core is non-conducting and 12 strands are there. Diameter of each strand is 0.25 centimeter. Outside diameter of the cable is 1.25 centimeter. So each strand diameter is 0.25, whereas outside diameter is of the cable is 1.25 centimeter, and there are 12 strands. So how to obtain the inductive reactance of the line, that we have to calculate. So here some geometric distances are given, how to obtain the values of the radius and the outer diameter of the cable. So these are all 12 conductors will be present here throughout the cable, because 12 strands are there. Then we have to apply the concept of geometry. If you apply the concept of geometry, you will be able to calculate the distances D12, D13, D14, D15, D16 and D17. These distances are very important because, as I said, the GMD and GMR calculation required you to know the geometric calculation between the conductors, which you have to calculate. The diameter of the non-conducting core is also required, which you have to calculate from the geometry, which is equal to 0.75 centimeter. Then the value of D11, that is equal to R dash, the 50 CS radius, which is equal to 0.7788 multiplied with the radius of individual conductor, which is equal to 0.097 centimeter. Now, once we have obtained the value of all the arrangements, now we can calculate the GMR and we can calculate the GMD. So mutual GMD is equal to the GMR, and the GMR and GMD calculation. So what is the distance between the each conductor? That is basically the GMD calculation and the GMR calculation. So you have to obtain the inductance first, that is equal to the calculation of ln of GMD by GMR, and then multiplied with 2 into 10 to the power minus 7. You will get the per phase inductance of the line multiplied with omega, that is 2 pi f. You will get the inductive reactance of the line. So these type of calculations require you to understand the geometry of the line first, and then the concept of inductances.